Hi, everybody, and welcome to Microfluidics 1. Today, we are going to talk about surface effects. Let's start with a short example. On the right-hand side, you can see a microfluidic chip, which is partially filled by a blue liquid. If we now start a video, you can see that the liquid moves through a microfluidic channel and until the chip is completely filled. However, there's no connection to an external pump. So how can the liquid move through the channel? And to understand this driving force, we have to understand surface effects. And these are the learning goals of our lecture today. So first, you should be able to mathematically describe pressures induced by surface effects. You should then also be able to categorize fluid behavior based on contact angles. And finally, if you combine both learning goals, you will be able to calculate the filling time of simple microfluidic structures, such as microfluidic channels. This lecture consists of 4 elements. There will be a video on surface tension and another one on contact angles. And there will be 2 examples that we calculate together. Let's start with surface tension. So what is surface tension and where does it come from? To understand the origin of surface tension, we have to take a microscopic look on the particles in different liquids. So let's first look at molecules that are far away from the interface between gas and liquid. The molecules far away usually interact with each other, and on every partner molecule is another liquid molecule. And that's why those molecules are in balance with their surroundings. If we now take a closer look on the molecules next to the gas-liquid interface, you might directly see that there's a difference. The gas molecules have another impact on the liquid molecules than the liquid molecules have on the liquid molecules. And this directly leads to a different force acting on the liquid molecules close to the gas molecules. This difference leads to 2 forces. The first force is one directing in perpendicular direction to the surface. So there's a force which acts in direction of the interface. And the second force that is a result of this imbalance is a tangential force in direction of the interface. And this tangential force is what we call surface tension. How can the surface tension be modeled? The surface tension is modeled as a proportionality factor for change in surface to change in surface energy. It is typically described by the Greek letter sigma. And here in this equation, you can see on the right-hand side the change in surface energy divided by the change in area. If you now insert typical values for both parameters, you will see that the unit of the surface tension is Newton per meter. So what would be the typical form of a liquid-gas interface? On the right-hand side, you can see 2 possible solutions. One is a spherical form, one is a cubic form. Which of those would be more probable? To answer this question, you have to understand the driving force for the interfaces. In general, the surface energy tends to be minimized. And this means that you will get a form where the surface is minimal for a given volume. And in this case, a sphere has at the same volume a smaller surface area. Let's do a simple calculation to check if this statement is true. Well, first we can calculate the surface of a sphere and the surface of a cube by standard equations. And then we can also calculate the volume of the sphere and the volume of the cube. And now we have 4 equations and only 2 unknown, because the volume is equal and we want to know which of those surfaces is smaller. So let's first calculate B independence of the radius, where B is the width of an edge of the cube. And if we insert this value of B into our area of the cube, we get this equation down here. And as you can see, is the area of the cube larger compared to the area of the sphere. So now we know the origin of surface effects, and we know about the typical shapes of gas-liquid interfaces. What we don't know yet is the pressure that exists because of the imbalance at the interface. And this pressure can be described by the Young-Laplace equation. So on the left-hand side, you have the pressure difference. On the right-hand side, you have the surface tension times kappa, which is the curvature of your interface. So what's the curvature of a surface? And for this, I've brought 3 examples. The easiest example is the curvature of a circle, because then it's obviously only the radius, 1 divided by the radius. If we now look at the curvature of a flat surface like that, like in a cube, you can see that the curvature is 0 because it's a straight plane and there's no curvature. And for the general case, for a random surface, you can calculate the curvature by building the gradient of the normal vector to the surface. If you now look closer at those values, you can directly see that flat surfaces don't result in Laplace pressure, whereas surfaces with curvature result in a defined value for the Laplace pressure, which acts in direction of the center of your curvature.